Hello everyone and welcome to the latest installment of the A-Level 9709 Solution Guide series. In this video we will take a closer look at paper 1.1 from the May-June exam period of 2021. So let's get right into it. In exercise 1 we are provided with the equation of a curve that is such that its first derivative is 3 over x to the power of 4 plus 32x cubed. It is furthermore given that the curve passes through the point 1 over 2, 4. We are supposed to find the equation of the curve. So in step 1 we need to integrate this expression, and to facilitate that process we will rewrite the fraction 3 over x to the power of 4, employing the laws of exponents provided. From there we can use for both summands the power rules for integrations, which are also provided. After simplification we can conclude so far that the curve can be expressed by the equation negative x to the power of negative 3 plus 8x to the power of 4 plus c. In our second step we need to find the value for c, and to do this we will make use of the information that the curve passes through the point a half 4. This means that f of a half equals 4, and therefore we can equate our solution from the first part of the exercise with 4. So all we need to do here is to substitute 1.5 for x, and from there rearrange our equation for c, delivering us its value, which is 12.5. So in the final step you just plug in this value into this equation to receive the equation of the curve, which is negative 1 over x cubed plus 8x to the power of 4 plus 12.5. Next on to exercise 2, where it's stated that the sum of the first 20 terms of an arithmetic progression is 405 and the sum of the first 40 terms is 1410. We are supposed to find the 60th term of the progression. Using the formula for summing an arithmetic series we can set up the following two equations, since it is given that the sum of the first 20 terms equal 405 and that of the first 40 terms 1410. Now with the assistance of this simultaneous equation we can work out the values for a and d. In step 1 we will divide both sides of the first equation with 10 and do the same thing for the second equation, the difference being that we will divide both sides by 20. Thereafter we can see that both of those equations have the expression 2a in common, which we will be able to exploit after we have rearranged both of those equations for 2a. Since 40.5 minus 19d and 70.5 minus 30d both represent 2a, we can now equate those two equations with one another to find our value for d, and after rearranging for d we will receive its value, which is 3 over 2. Now we can take this value to find out the value for a. We can either substitute d for 3 over 2 in the first or in the second equation. I've opted for the first one for no specific reason other than that the values here are smaller. So after doing so we can easily figure out the value for a, which is 6. From there we now have the chance to find the 60th term of this progression, applying the arithmetic sequence rule provided, and after plugging in the values for a and d into the formula we can conclude that the 60th term of this arithmetic progression has the value 94.5. Moving on to exercise 3, where in part a we are supposed to find the first 3 terms in the expansion 3 minus 2x to the power of 5 in ascending powers of x. This can be achieved with the assistance of Pascal's triangle provided. Here it is sufficient just to take a look at the first 3 summands of the expansion of this term, since we are only required to find the first 3 terms of the expansion in ascending powers of x. Since x occurs in the second summand and not in the first, we can rest assured that the first 3 terms will automatically appear in ascending powers of x, since 3 could be written as 3x to the power of 0. After simplification we can conclude that the first 3 terms of this expansion in ascending powers of x are 243, negative 810x, and 1080x squared. In part b of this exercise we are required to find the coefficient of x squared in the expansion 4 plus x squared multiplied 3 minus 2x to the power of 5. Since we have already discovered the first 3 terms of the expansion of the latter part of this multiplication, we just need to focus on expanding the first bracket, which after applying the whole square formula leads us to the conclusion that the expansion of it equals 16 plus 8x plus x squared. In the second step we will simply multiply this expression with the first 3 terms of the expansion of exercise A, and from here just focus on all of the summands containing the expression x squared. From here we just have to add up all of their coefficients, namely 17,280, take away 6,480 and adding 243 to it, letting us conclude that the coefficient tangent of x squared is 11,043. Moving on to exercise 4, where we are provided with a part of the graph of y equals a multiplied tangent x minus b plus c. Furthermore, it is given that b lies within the interval of 0 and pi, and we are supposed to state the values of the constants a, b, and c. This can be performed by using our knowledge concerning the amplitude, period, and phase shift of trigonometric functions provided. In our specific case, c represents the vertical shift of the graph, which in this case is +1. The reason being that the inflection point of this curve occurs on the line y equals 1. To determine b means focusing on the graph's horizontal shift. If there were no horizontal shift, the inflection point would go right through the y-axis, and the shift away from the y-axis is exactly a quarter pi. Finally, to determine the value for a, we can now make use of the results that we have found for the values concerning b and c, and substituting their values accordingly with the variables from aforementioned formula, and replace the variables x and y for a point that we can clearly identify from looking at the diagram above. In this case, I've chosen the point pi over 2, 3. Rearranging this equation for a delivers us the amplitude of this tangent function, which is 2. Next on to exercise 5 of this exam paper, where we are dealing with a geometric progression. It is stated that its 5th, 6th, and 7th terms are 8k, -12, and 2k respectively. It is additionally given that k is negative, and we are supposed to find the sum to infinity of the progression. So at first we will write down all of the information that was provided from this exercise, namely the value of their terms, which enables us to calculate the common rate r. To identify a successor of a term of a geometric progression, let's say an, we note that we just have to multiply it with r to receive the value for its successor. This wouldn't do much in our case though, since whether or not we were to divide the 7th term by the 6th term or the 6th term by the 5th term, it wouldn't help us in finding the common rate. To do that, we would have to find a way of eliminating k, and this can only be done if we were to divide the 7th by the 5th term. Furthermore, we need to keep in mind that if the successor of a term can be determined by an multiplied r, its successor in turn can be found by multiplying our original term with r squared. Therefore, we will set up the following equation and rearrange it for r, which in our case must be 0.5, since its value can only be larger than 0. From here we can now find our value for a, namely by exploiting the fact that an can be found by multiplying a with the common ratio to the power of n minus 1. We can substitute r for 0.5, which we have determined in our previous step, and from here we just need to rearrange our equation for a, which delivers us the first term of this geometric progression, which is -384. Now we have found everything that we need in order to determine the sum to infinity, namely the value for a and the value for the common ratio, and after plugging in those values accordingly into the formula, we should be able to conclude that the sum to infinity of our geometric progression is -768. Moving on to exercise 6, where we are provided with the equation of the curve, namely y equals 2k minus 3 multiplied x squared minus kx minus in brackets k minus 2, where k is a constant. The line y equals 3x minus 4 is a tangent to the curve, and we are supposed to find the value of k. The line being a tangent to the curve means that the line touches the curve in exactly one coordinate. So to find the point that the curve and the line have in common, we simply equate the equation of the curve with that one of the line. What we will do is we will arrange this for 0 and then further in a way that it resembles the shape of a quadratic function. Therefore, we can conclude that a, the coefficient of x squared, has the value 2k minus 3, the coefficient of xb -3 minus k, and the constant c 6 minus k. At this stage, we are now able to employ the quadratic formula in order to find our solutions. Since we are aware of the number of solutions already, which is exactly 1, as the curve touches the tangent or vice versa, we need to ensure that the determinant equals 0, which provides us exactly with one solution. So we are equating the determinant with 0, which can be identified with the quadratic formula provided. At this stage, we simply plug in our values for b, a, and c into this formula. In step 1, we will employ the whole square formula. Please keep in mind that if if both components are negative, it behaves as if both of them were positive. Therefore, we will only find positive values at this stage of our equation. And in the latter part of the left-hand side of the equation, we will simply expand both brackets by multiplying all of those elements from the one bracket with those of the other bracket, whereby 15k is already the simplification of 2k times 6 being 12k plus 3k, which we would get after multiplying negative 3 with negative k. Thereafter, we will step by step simplify the equation and realize that this term represents the expansion of the whole square formula, and after taking the square root we can easily conclude that the value of constant k is 3. Next, on to exercise 7, where in part A we are supposed to prove the following identity. To get an idea on how we can make this work, we see that on the right hand side we are working with tangent square theta. In the numerator of the fraction to the left hand side we are working with sine squared theta, and the same occurs for the denominator. We should remember that sine squared theta over cosine squared theta. So in step 1, working with the trigonometric identity after Pythagoras provided, we will rewrite the denominator as follows. In the next step, we will expand the expression of the numerator. So negative sine squared theta is the same as negative sine squared theta minus sine squared theta. Thereafter, we will dissect the left-hand side of the equation into two separate fractions, keeping in mind that according to the same rule that we have employed on the outset of the exercise, we can rewrite this part as cosine x, which will allow for us to simplify this part of the left-hand side of the identity to 1. Additionally, again according to trigonometric identities provided, we know that sine squared theta over cosine squared theta equals tangent squared theta, and after all is said and done, we can conclude that the fraction to the left-hand side as well as the expression to the right-hand side are indeed identical. In part B of exercise 7, we are now hence supposed to solve the following equation for theta being within the interval of 0 and 180 degrees included. From part A of this exercise, we know that the left-hand part of the equation is identical to the expression 1 minus tangent square theta. So we will rewrite this equation accordingly and rearrange it for 0. At this stage, we should realize that we are provided with a biquadratic function, since the power of this tangent is the power of the second tangent multiplied by 2. 2 multiplied 2 being 4. Therefore, we will substitute tangent squared theta for x, which provides us with the opportunity to work with the quadratic formula. After plugging all of our values in accordingly, we can conclude that the value for x is either negative 1 or 1 over 2. In order to now determine our values for theta, we now have to perform a resubstitution, and since tangent squared theta can never contain a negative value, since any number squared delivers us a positive number, we only have to investigate the equation 1.5 equals tangent squared theta. After taking the square root on both sides of the equation, we are provided with two solutions, the first one being 35.3 degrees, and the second can be found using the reference rules for angles provided, and can conclude that the size of the second angle must be 144.7 degrees. Next, on to exercise 8. Here we are provided with a diagram that shows a symmetrical metal plate. The plate is made by removing two identical pieces from a circular disc with center C. So those two semicircles have been removed in addition to those parts of the circle. The boundary of the plate consists of two arcs, namely PS and QR, both of which are of the original circle, and two semicircles with PQ and RS as diameters. The radius of the circle with center C is 4, and PQ and RS are also 4. Since PQ and RS are 4, the diameter, we can conclude that the radius of both of those semicircles is 2 units long, since the relationship between a radius and the diameter of a circle is that the diameter is twice the size of the radius of a circle. So all of this information has already been incorporated into this graph. In part A of this exercise, we are supposed to show that angle PCS, which is this one here, has the value of 2/3 multiplied pi radians. To find this inner angle, the following can be done. We know that since this metal plate is symmetrical, it's not just symmetrical vertically but also horizontally. We can establish that both of those right triangles here are congruent. Therefore, we need to find out the size of this angle, which we can, since we are aware that we are working with a right triangle, and we know the size of its hypotenuse as well as the opposite size of the angle, which enables us to work with the sine rule for right angles. I've named this midpoint between P and QM. Therefore, to establish the sine of the angle PCM, we need to divide the hypotenuse from the opposite, which equates to 2/4, and we can simplify this down to 1/2. With the help of our pocket calculators, we should establish that sine PCM has the value pi/6. While establishing this result with the help of your pocket calculators, please keep in mind to set it to radians if you haven't done so already, since you would otherwise receive a wrong result if you have stayed in the degree mode. Since this angle is of the same size as that angle, we can now subtract 2 times pi/6 from pi, since this entire angle here is of the size 180 degrees. But since we are working in radians, we should keep in mind that 180 degree is represented by pi radians. Therefore, we can conclude after simplification that the angle PCE is indeed 2/3 multiplied pi radians, which was to be shown. To determine the exact perimeter of the plate, we can think about this problem as follows. Firstly, those two semicircles, due to symmetry, are identical, therefore forming a whole circle. So what we can do here is we can find the perimeter using the formula provided, and we can substitute r for 2, since the radius of this circle is 2 centimeters long. As for PS and QR, we know that those two arcs, again due to symmetry, are of identical length. So what we can simply do is to calculate either the arc line for PS or for QR, which is the same, and multiply its result by 2. The arc line can be calculated as per the formula provided. So since this arc line occurs twice, we multiply aforementioned formula by 2. Simplifying the diameter of the two semicircles equals 4 pi, and doing the same thing for the two arc lines delivers us the value of 16/3 multiplied pi. In the next stage, we will multiply the numerator and denominator of 4 pi/1 with 3 to be able to put all of the summands onto the same fraction, and after simplification we receive the exact length of the perimeter of the plate, which is 28 pi/3. In the final part of this exercise, we are supposed to show that the area of the plate is 20/3 pi plus 8 multiplied the square root of 3 square centimeters. To do that, we will subdivide the disk into the following components. Firstly, we can see that it consists of a rectangle, PSRQ. Secondly, of two circle segments, both of which are identical, and from there we subtract the area of the small circle, since both of those indents are in the shape of two identical semicircles stitched up together deliver us a full circle. To achieve that, we first need to find the length of PS or QR respectively. To find PS, we will work within the triangle CPS, and in order to determine PS, we will employ the cosine rule, since we know the length of both legs, which are each 4 centimeters long, and in part A of this exercise we have already determined the size of this angle in radians. Employing the formula as provided and plugging in the values for the variables accordingly, we will be able to conclude firstly that PS squared equals 48, and after taking the square root on both sides of the equation, we will be delivered with the result of the square root of 48, which is equivalent to 4 times the square root of 3. It is desirable to transform the square root of 48 into this expression, since it is our goal to show that the area of the entire plate is something that's related to the square root of 3. So now we have everything that we need in order to execute our formula/concept from the outset of this part of the exercise. Therefore, to determine the angle, we multiply PS with 4, since the distance from P to Q is 4 centimeters long, and in order to determine the area of a rectangle, we multiply its length by its width. To determine the area of both of the circle segments, we can calculate the length of one of their arcs employing the formula provided and multiplying everything with 2, since this circle segment occurs twice, here and there. And finally, we can subtract the size of the full small circle, which is pi r squared, r having the value 2. From there we can simplify our expression step by step, while keeping in mind that pi needs to be represented using a fraction having a third in its denominator, so we will keep all of that intact. And the same occurs for our constant, which needs to be expressed in terms of the square root of 3. So in our penultimate step, we will make sure that everything in terms of pi and everything in terms of our constant is grouped together accordingly. And since 32 pi minus 12 pi equals 20 pi, the denominator beta in both cases being the same, and 16 minus 8 equals 8. We have shown that the area of the plate is indeed as mentioned on the outset of this part of exercise 8. Continuing with exercise 9 of this exam paper, where functions f and g are defined as follows, whereby a is a constant. In part A, we are supposed to state the range of f. We know that f is only defined for x being 2 or larger, therefore we will insert the value of 2, since this entire expression will be smallest for that value, as 2 minus 2 equals 0, and only negative 4 would remain. For any value for x that is larger than x, this expression would be positive, and a positive number minus 4 will deliver us a number that is larger than negative 4. So after having substituted our variable x for 2, we can conclude that the range of f is negative 4 or larger. In part B, we are supposed to find the inverse of function f, which is done by substituting x for y and vice versa, keeping in mind that f of x can be rewritten as y. From here we will have to rearrange this equation for y, which is done by firstly isolating the term in brackets, since this is the one that contains y. After having done so, to eliminate the power of 2, we will take the square root on both sides of the equation, and in the final step we add both sides of the equation with 2 in order to isolate y, providing us with the conclusion that the inverse function of f can be described with the square root of x plus 4 plus 2. In part C of exercise 9, it is given that a has the value negative 5/3, and we are supposed to solve the equation f of x equals g of x. So what we will do is just equate both of those equations, whereby we will substitute a for the value provided within this exercise. Firstly, we will expand the first bracket using the whole square rule provided, and then simplify and rearrange this quadratic expression for 0, enabling us in this case to follow through with the reduced quadratic formula, as the coefficient of x squared is 1. Using the formula provided, and after simplifying our equation, we will be able to conclude that x is either negative 2/3 or 3, but since, as per definition, since f of x is only defined for x being 2 or larger, we can conclude that this equation is solved only for x equals 3. Next on to part B of this exercise, where it is stated that given instead that g of the inverse of f of 12 is 62, we're supposed to find the possible values of a. In step number 1, we will find g of the inverse of f by substituting x in g for this expression here. In the second step, we will now substitute this entire expression for x in g of x again. Thereafter, we substitute x for 12 and simplify the left-hand side of the equation from inside out, meaning we will first attempt to simplify this thing here. So in the first step, to simplify the left-hand side of the equation, we will work all of those brackets from inside out. So the inner brackets simplify to 6, and then from there we can multiply 8 with the term of these brackets, and since 4 plus 2 equals 6, 6 multiplied to a leads us to 6a. Those two remain, and the remaining summed with the value of 2 will be subtracted from 62 on the right hand side of the equation. Thereafter we will expand those brackets and bring 60 to the left hand side of the equation. Instead, we could also just have subtracted 62 from both sides of the equation at this stage. At this stage here, we can just simplify our equation a little bit. It's not necessary, but it's a personal preference of mine to work with integers that are as small as possible. Regardless, we will be working with the quadratic formula to determine our values for a, and plugging in 3, 1, which is the coefficient of a, and negative 30 according to the formula provided. We can simplify and conclude that a can contain either the value of negative 10/3 or 3. This brings us to exercise 10 of this exam paper, where we are provided with the equation of a circle as follows, and in part A we are supposed to find the x-coordinates of the points A and B where the circle intersects the x-axis. To execute that, we need to keep in mind that the x-axis is represented by the line y equals 0. So in order to find the intersection of the circle with the x-axis, we simply equate this line graph with the equation of the circle. In this case, this is easiest done in substituting 0 for y within the circle equation. After simplification, we are receiving a simple quadratic equation, which we can solve using the reduced quadratic formula provided, since the coefficient of x squared is 1. Following through from there, we are receiving the requested x coordinates, which are -7 and 11. The y values which were not required are of course 0 in each case. The reason for that every point that lies on the y-axis has 0 for its y coordinate. Moving on to part B of this exercise, where we are supposed to find the point of intersection of the tangents to the circle at A and B. So what we are roughly looking into from a visual point of view is, let's imagine that this is our circle which intersects the y-axis. So we will put the tangent at both points A and B to the circle, and those two tangents will intersect at the point I for intersection. So this is what we will have to determine here. So firstly, what we need to do is to find the center of the circle, for which we will have to complete the square for our x's and our y's. This is done using the formula provided. So at this stage, this will refer to this square, x minus 2 squared, and this part also refers to a whole square, namely y plus 3 squared. Finally, we will have to add up the following constants and bring those to the right-hand side of the equation, representing r squared. Therefore, the center of this circle is located at 2, -3. From exercise 10a, we are also aware that points A and B are located at those coordinates. From there, we will have to find the gradients of AC and BC, the reason being that the radius is at a right angle to the tangents. Using the formula provided, the gradient of AC can be identified as -1/3 and that of BC as +1/3. The gradients of the perpendiculars can be found using the formula provided, and knowing the gradients of the tangents, we can now set up their linear equations in the form y equals mx plus c. So on the left hand side, we will be working on the linear equation of the tangent through point A, and on the right hand side to that one through point B. Firstly, we will be substituting 3 and -3 respectively for m, and we will substitute y and x with the coordinates of A and B. Rearranging both for y will provide us with the linear equations. To now find the intersection point of both of those tangents, we simply need to equate the equation of both of those lines. Doing so will allow for us to find the x coordinate, which after simplification turns out to be 2. And lastly, to find the y coordinate of aforementioned intersection point, we can either substitute 2 for x in this or in this equation. In this case, I opted for the tangent that goes through point A, and we are receiving 27 in return. Therefore, the intersection point is located at the coordinates 2, 27. We've now arrived at the final exercise of this exam paper, exercise 11, where we are provided with the equation of a curve, which is y equals 2 multiplied the square root of 3x plus 4 minus x. In part A, we are supposed to find the equation of the normal to the curve at 0.44. We are supposed to provide our answer in the form y equals mx plus c. To find the normal to the curve at x equals 4, we will have to identify the gradient there, which is done through with the help of the first derivative of our function. So to find the first derivative of the curve, we can firstly ignore the factor of 2. And for the term in brackets, we will have to work with the chain rule provided, meaning that we are working with the combination of the power rule, which means that we will have to employ the power rule twice, namely once for the term in brackets and once for the term 3x, which is 3, and the derivative of -x is simply -1. After simplification, we will come to the conclusion that the first derivative is represented by the expression 3 multiplied 3x plus 4 to the power of -1/2 minus 1. To find the gradient of the tangent for x equals 4, we simply substitute 4 for x in this equation and find that the gradient of the tangent equals -1/4. So graphically, what we can imagine is we are provided with a curve, we have the tangent and the coordinates 4, 4, and we are supposed to find the normal, which is perpendicular to the tangent at this point. In order to find the gradient of the perpendicular, we can work with the formula provided, receiving 4 for its value. What is now left for us is to find the value for the y-intercept, for which we can make use of the fact that the normal to the curve goes through 0.44. Therefore, we will substitute x for 4 and y for 4 as well. Rearranging this equation for c delivers us the the y-intercept of the perpendicular. Therefore, it can be described using the equation y equals -1/4 x minus 12. In part B, we're supposed to find the coordinates of the stationary point, which translates into having to equate the first derivative with 0. Since we've already found the first derivative in part A of this exercise, we can simply recycle our result and equate it for 0. To be able to eliminate the exponent, we will firstly isolate the expression in brackets by adding 1 and thereafter dividing both sides of the equation with 3, delivering us the following equation. At this stage, we can square both sides of the equation, and keep in mind that the negative sign means that we have to find the reciprocal of the expression within the brackets. To eliminate both of the denominators, we can simply cross-multiply both sides of the equation, and after simplification, we will be able to conclude that the x-coordinate of the stationary point is 5/3. Finally, to find the corresponding y-coordinate, we simply substitute 5/3 for x in the equation of the curve, receiving 13/3 as the value for our y-coordinate. Thus, our stationary point is located at 5/3 and 13/3. Part C requires from us to determine the nature of the stationary point, meaning that we should find out whether or not the stationary point represents a minimum or a maximum. And to do this, we will firstly figure out the second derivative of the curve, for which we can follow through starting from its first derivative. Again, we are dealing with a factor in front of the expression in brackets, which just remains as is, and we will be working again with the chain rule provided. After simplification, we will be receiving the expression -9/2 multiplied in brackets 3x plus 4 to the power of -3/2. So our results consists of two factors, namely -9/2 and the expression and everything else. -9/2 is obviously less than 0, so this part is negative. Since we know that the x-coordinate of the stationary point is 5/3, we can simply substitute this for x and determine from there that this expression is larger than 0. And we know that a negative expression multiplied a positive expression provides us with a negative number, and therefore we can arrive to the conclusion that the nature of the stationary point is that it represents a maximum. Lastly, to conclude this exam paper, we are supposed to find the exact area of the region bounded by the curve, the x-axis, and the lines x equals 0 and x equals 4. Two of the lines being x equals 4 and x equals 0 provide us with the upper and lower boundary of our area. So in the following step, we need to integrate the equation of our curve, which is done using a combination of the power rule and the chain rule. Now we need to counteract the coefficient of x within the bracket, which is 3, and to do so we will multiply it with its reciprocal, since a number multiplied with its reciprocal always equals 1. For the latter part, we will just have to employ the power rule as provided. Thereafter, we will simplify our expression a little bit and then plug in the upper and lower boundaries and substitute those for x, delivering us the solution that the exact area of aforementioned region is 16 and 8/9. I've been your host Marco from PlanetMaths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.